the attendance form yet. No, the link for the Google form is posted and pinned in the chat box. So kindly check if you haven't done so. All right. Okay, so we move on to our next topic, no, which is the amplifier circuit. So this is just a relatively short discussion on the specific applications or related concepts, no, in the amplifier circuits. Should we go through frequency response? Okay, so we will just go through the transistor amplifier circuit analysis. Okay, so okay, so from the previous section, you only determine the gain of the transistor amplifier with input and the output connected directly to the terminal of the transistor. No? In this module, we will analyze the effects of the source resistor and load resistor, the single stage and multi-stage amplifiers. The calculation of the individual effects of load resistor and source resistor will also be covered, no, in this discussion. So you know the effect of RL and RS and the calculations for the effect of the um, said resistors in the voltage gain. No? Okay, so we will also cover cascaded configurations. Right, so all parameters determined in the previous lecture are for the unloaded amplifier whose input voltage is connected directly to the transistor. So the circuits below is a typical network with unloaded voltage gain specified in the previous discussions. So we've seen here, no, the unloaded circuit, and then we will go through with the analysis with the load effects and the source effects, source resistance effects. Now, when source is added to the circuit, we can now derive the new voltage gain by simplifying the circuit further. No? So we have the source voltage here and the equivalent Ri as part of the input impedance network, and then ZO is or RO is part of the output impedance circuit, and then the no load voltage gain and is the condition where only the RO is considered. The voltage gain for this configuration is the ratio of the output voltage to the source voltage, VR over Vs. In general terms, the voltage gain or the no load voltage gain is VO over VI. Using the voltage divider theorem, the effect of RI and RO can be simplified as the following. Okay, so VI is equal to Vs, voltage source, and the effect is the result of the voltage across the Ri as divided by the sum of Ri and Rs. Voltage divider, no? Same as the DC analysis that we've done earlier. For the general term of the voltage gain, we have VO is equal to VI times the gain no load no load voltage gain AVNL. Substituting the equation for Ri for Vi, we have the VO as the no load voltage gain times the source voltage and then the voltage divider factor Ri divided by Ri plus Rs. Getting the equation for AVS O, no voltage source. We have VO over Vs and is equal to no load voltage gain times the factor from the voltage divider network Ri divided by Ri plus Rs, where AVSO is the gain with the effect of the source resistor load. The circuit below will be used to analyze the effects of the load resistance but without the source resistance. So we can perform separate analysis for such cases. The unloaded gain will change because the output impedance of the system is in series with RL. Using the generalist equation for AV, the output voltage will now be measured across the load resistor. So the voltage across RL in terms of AVNL, no load voltage gain, is yeah. So the voltage across RL is the VO, which is the VI times no load voltage gain, and then yung voltage divider, right? RL divided by the sum of RL and RO. And since no load voltage gain is equal to VO over VI, simplifying this thing, we can cancel out the VI factors here. No load voltage gain, loaded voltage gain can be related. No? So loaded voltage gain is equal to no load voltage gain times the effect of the uh, voltage divider network. So what does this tells us is that if RO is significantly uh, small, then we can just get rid of this network or approximate this network, right? Or RL is significantly large, that it will sort of shadow the effect of RO. Okay, so to analyze the effects of both source and load resistance, we go back to the uh, two-pin input-output model, no? And then perform separate loop analysis for again for the input loop and the output loop using the general equation for the voltage gain. AV is equal to VO over VI. The output voltage is measured across the load resistance while the input voltage is measured across the input impedance of the AC network from the source voltage. With the effects of both RL and RS, the voltage gain is and AVS is equal to VO over VS is equal to VO over VI times VI over VS. Since VO is equal to V cross the load resistance RL right here, na? So we'll use the same no load voltage gain times the VI, and then the voltage divider factor RL over RO plus RL. And since VI is equal to RI divided by RI plus RS times VS, so it's just numerous rounds of um, voltage divider applications, right? VS is equal to uh, RI plus RS over RI times VI. So we just parang reverse this thing to be able to come up with the BS figures. Using the substitution, we substituted the no load, the VO here and the VI here. So loaded voltage gain is equal to yeah, so AVS is equal to uh, no load voltage gain times the two uh, voltage divider factors. RL by virtue of the voltage divider here, and then RI by virtue of the voltage divider here. So dalawa. So twice the effect, no? The effect of the voltage divider here and the effect of the voltage divider here. Was it simplified further? So the loaded voltage gain figure here times the RI RS voltage divider. So example, okay. So for the given circuit, and so we have we solve for the loaded voltage gain and the effects of the source resistance. Okay, so example one showed that no load voltage gain is 280, input impedance is 1.7K, 1.07K, output impedance is 3K, RL is at 4.7, and RS is at 0.3K. So loaded voltage gain is no load voltage gain times the voltage divider network from the output side, RO and RL. So the 20 negative 280 voltage gain was reduced to 170. So it has a de-reduction effect. The loading effect has the reduction effect in the voltage gain. The source effect naman is the loaded voltage gain times the voltage divider factor considering RO and RL, or sorry, RI and RS rather. Yeah, so the negative 280 voltage gain was reduced to negative 170 with the loading effect, and with the source effect was reduced even further to negative 133. A quick summary of some various configurations can be seen here. For the fixed bias, you have the RL, RC, and R0, RE. For the voltage divider bias, what is essentially changed here is that RB is also essentially replaced by the R1 and R2 parallel equivalents. So, and then in this guy's common emitter here, common base, and then the unloaded effects. In the unloaded effects, we have the RE in the RO calculation. So further configurations in the feedback resistance. So quick summary. So the RS mentioned is the internal resistance of the voltage source. For FET naman, use the variable R sig for the source resistance. Take note that the load resistance appears in parallel with the drain resistance. So we're using the notation R sig, so as not to confuse uh, with the RS sa side ni source, because we have the RS here. So instead, we're using R sig notation. The load resistance appears in parallel with the drain resistance, and the source resistance R sig appears in series with the gate resistance. Loaded voltage gain is equivalent to the transconductance times the parallel resistance equivalent of internal RD, external RD, and load RL. For the overall gain, AVS, that's the loaded voltage gain times the voltage divider factor, R sig and RG right here. Which for most applications, if the gate resistance is significantly larger than the R sig, same thing. Approximation can be applied. For the output side, if load resistance is significantly larger than the drain resistance, or the internal resistance RD rather is significantly larger than the effects or the parallel equivalent of RD and RL, the results will be that it can be approximated as a factor of RD and RL, or the RD value, internal RD value can be omitted. So here we have the summary. Okay, you can include this in your review to determine the effects for the various other configurations. So last topic is the cascaded systems. Okay, so the two-port systems approach has been useful for us in analyzing response characteristics, of AC analysis. But of course, we can use it further for presenting systems connected to each other. So a cascade system is consists of individual stages. No? For this example, we have n stages, and each stage is an amplifier having the respective gains AV1, AV2, AV3, and so on, under the loaded conditions. AV1 is determined by the input impedance of AV2, acting as the load resistance of AV1. Okay, so input impedance of AV2 is the load resistance of AV1. Same as AV2 to AV3. Yeah. So input impedance of AV3 is the output impedance of AV2. Input impedance of AV4 is the output impedance of AV3. So the total gain of the system is determined by the product of the individual gains. You just multiply everything for AV1, AV2 up to AVN. Equivalent network model shown below will be used for better analysis and getting the overall gain of the cascaded network. Overall gain is equivalent to, so total voltage gain is R1 over R1 plus RS. So same voltage divider equivalent. R1. Considering the circuit shown by DC analysis, we can determine the value of each individual emitter current to be used on small signal analysis. So we have two fixed bias, cascaded, no? We can perform analysis separately, no? Separate natin siya, but this can be analyzed in combination. So IE is the current for the first stage, emitter current for the first stage here. We don't have emitter resistor. IE2 is the emitter current here. Same thing for the second stage, we don't have the emitter resistor. By DC analysis, the individual stage parameters are calculated. RE1 is, we'll use the same 26 millivolt factor. Input impedance, ZI, is for the first stage. Output impedance of the first stage is ZO1. No load voltage gain 1 is for the first stage. For the second stage, we use the same calculation for RE equivalent. ZI2 is the input impedance of second stage. ZO2 is the output impedance of the second stage. And AVNL2 is the voltage gain of the second stage. Computing for the individual gain, looking at the network with effects of the load resistors, we have the following. AVNL1, or the voltage gain of the first section is AVNL1, and then your input network here, no? RI and RS, and RI and RO rather. No? AVNL2 is RL and RO circuit right here. So we have RI, RO here for the first section, RI, RL and RO2 here for the second section. And solving for the total gain of AV is just the combination of this AV1 and AV2. The overall voltage gain of the cascaded system is AV total times RI1 divided by RI1 plus RS. The network, the voltage divider network right here. Okay, so the two-stage system employs the transistor emitter follower configuration prior to a common base configuration to ensure the maximum percentage of the applied signal appears at the input terminals of the common base amplifier. In the figure, the no-load values are provided for each system with the exception of ZI and ZO for the emitter follower, which are the loaded values. For the configuration of the figure, then we will solve for the loaded gain of each stage and the total gain, AV and AVS. So for the last calculation, and for the emitter follower configuration here, all right, so VO is equal to VO1, no? For the first stage is equal to ZI over CI plus ZO, DI plus ZO, times the no load voltage gain. So gain of the first stage is determined to be at 0.684. Very small, no? Because again, this is an power configuration. It is intended for a different application. It has a low voltage gain, but in most cases, it will have a high current gain. So the DC analysis is omitted, but that is usually or essentially the purpose. For common base configuration, VO2, right, here is equal to no load voltage gain of the second section times the uh, voltage divider network RL and R0, internal resistance R0. So it is determined to be, we just skip to the values, AV2 is at 147. So relatively higher for the common base. Okay, so this is essentially the function of the common base, no? To provide the sufficient voltage gain characteristic. Total voltage gain is 0.68 times 147. So it's at 101.2. With the loading effect in the source or the input side, yan, so we have another voltage divider network here. It was reduced further to 92. And so the total gain is the product of the gain of each stage, including the loading effects of the following stages. So for FETs, AV total AV1 times AV2 for higher, more number of sections, just keep on going, AV3 and so on. But again, for the case of FET, we have the transconductance and the RD values for its stages. So the overall gain is GM1 times RD1 times GM2 RD2. So what happened when we perform the cascade configuration? The inverting characteristics of the common source configuration was neutralized. So it became a non-inverting amplifier. So from this configuration, we can gain that insight. Now we can, if we want an in-phase amplification, if we don't want the signal inversion, we can cascade an even number of amplifiers and it will result to a positive gain value. It will counter the inversion of the common source characteristics. Same as in the case of BJT, if we want a non-inverting amplifier, we can cascade an even number of common emitter amplifiers. Okay, so that's the hopefully the insight that you can remember out of these calculations. And that's pretty much our lecture for today. So I'll finalize an announcement regarding the midterm exam, but much of it will be online MCQ setting. Some problem solving will be involved. So kindly review all the exercises presented in our materials. The total gain of a multi-stage amplifier is the product of the individual gains. Single-stage amplifiers can be connected in sequence with capacitively coupled and direct coupled configurations to form multi-stage amplifiers. The gain obtained with the source resistance in place will always be less than the obtained under the loaded or unloaded conditions due to the drop in voltage across the source resistance. For same configuration, no load voltage gain is less or is greater than the loaded voltage gain, and which is even greater than the gain with the source effects. For particular design, the larger the value of RL, the greater is the level of AC voltage gain. For a particular amplifier, the smaller internal resistance, the signal source, the greater is the overall gain. For any network that has coupling capacitors, the source and load resistance does not affect the DC biasing levels. So that's it for our discussion today. Again, kindly check the attendance sheet. The form is already posted, or the link to the form is already posted in the comment section. So I'll close the forms by siguro around 11 a.m. So kindly accomplish the form within the prescribed duration. So any questions, concerns, or clarification so far? If none, can I see a show of hands if everything is clear up to this point? Questions? Yes. Okay. So I'll share the slides later and post some specific announcements covering the conduct of the midterm exam within the week. And if you have further questions, concerns, or clarifications, just feel free to send me a message. And then I'll see you guys. Teka, so I'm thinking of ano no the usual schedule, like what happened in quiz 2 is on a Saturday afternoon or evening. So last time there was some conflict of schedule with the other guys, who were affected. Yeah, quiz 1 was from 6 p.m. to 8 p.m. So the tentative schedule for now, because some groups are not able to join the 6 to 9. It will be 2. Actually, I will require supposed to require 3 hours here. So I'm not sure if it's okay with you, no, but I'm thinking of 7. Medyo late, no. The result will be a little later, just to synchronize everything. So, but if there will be no objections, I'll try to push through with the midterm exam schedule. So this is proposed for now. If no objections, then the proposed midterm exam schedule will be on April 5, Saturday, and that will be from 7 to 10 p.m. Medyo late siya, but this is the schedule that will be able to cover all the other schedules and even the irregular blocks. So yeah, so that's the proposed midterm schedule for now. I'll post a separate announcement if this will be finalized. The coverage will include all the topics that we have covered so far. So I guess that's it. And if you have further questions, concerns, or clarifications, just feel free to send me a message in the Google, email, or chat will do. I'll try to address your concerns. All right. So that's it. And I'll see you guys next week, and have a great week ahead.